All right, so we're jumping to section 11.5, 11.4. All right. So we're going to do the sections a little bit out of order. So I think the order that we're doing them in makes more sense than the way they're in the book. So today we're going to talk about the volume of prisms and cylinders. Spell it correctly. All right. So what do we mean by the volume? So something inside. What's the difference between volume is an area? How much can go inside? What's the difference between volume and area? Areas for two-dimensional shapes, volumes for three-dimensional shapes. So volume, we can think of volume as how much space inside a 3D shape. So that's what we're talking about when we're talking about volume. The first thing I want to talk about, one thing that makes volume a little easier is this. It has a named after a very nice name. Cavalieri's principle. So here's my question about Cavalieri's principle. So I have a stack of books here, and we can say the volume of this stack of books is essentially 5 books, right? Does it change? Does the volume change how much space is taken up if I do this, if I slide them like so? No, there's still 5 books. This has the same base, the same height. The base is the shape of one book. The height is five books high. So it has the same base and the same height. But it has the same volume. Well, this is a right rectangular prism, and this would be a model of an oblique prism. Does it change if I did some books that way and some books the other way, so I make kind of a V shape? That doesn't change the volume, does it? I could do them back and forth. The volume's still 5 books. And I could, this would be my cylinder. So my slinky's a cylinder. If I filled it with water, it would hold a certain amount of water. Does it change if I do this? Slide it sideways? Making an oblique cylinder? No, it doesn't. Because it's still, and it has the same base and the same height, but it's still however many rings make up the slinky, that's how much space it takes up. I could do it back and forth. I could make the shape, all kinds of crazy different shapes. Still the same volume. So that's what Cavalieri's principle tells us, is that if we have a solid with, and we're saying that it stays the same shape, so it's still, so this is a circular all the way up or rectangular all the way up. The shape doesn't change as we move up a solid. So solid with the same base and height. Have the same volume. That's what Cavalieri's principle tells us. We can change the shape of the slinky as long as we're not making it skinnier in the middle. So it's not shaped like a base. I can make it oblique, or I can make it right, and it has the same volume. And essentially, it says oblique prisms, oblique cylinders have the same volume as right prisms and right cylinders. And Cavalieri's principle will work for other shapes that we're talking about also. So what's nice about that is the volume of any prism or any cylinder, we can use the same formula. If you remember back when we talked about surface area, our surface area formulas only work for right prisms and right cylinders. All right, so let's get to our formula. The volume of any prism. Can be right, can be oblique, can be any crazy shape we want. The volume is nice easy formula. Base times height, where B equals the area of the base and H equals the height. Our key here, just like when we're talking about surface area, our key is the area of the base. We have to find the area of the base. If our base is a triangle, we have to find the area of the triangle. If it's a trapezoid, we have to find the area of the trapezoid. If it's a parallelogram, we have to find the area of the parallelogram, etc., etc., etc. So the base is really our key. But it's a nice, easy formula. All right, so let's start off with an easy example. We want to find the volume. All right, here's my... There, the volume's 10. That's the volume knob. It's turned all the way up to 10. So there's 9 here, and there's 8. That's your little volume knob. So the volume's turned all the way up to 10. Have you guys ever seen Spinal Tap? They talk about the volume of their amps going up to 11 because it's higher than 10. All right. All right. You guys got all serious over the weekend. Yeah, you need to be a calculus student. Lighten everything up.
You didn't invite us.
You have to be you take calculus. You can go. All right, so there's our prism. What kind of prism is this? Rectangular prism. It's close to being a square, but it's not quite a square. So I'm going to draw in the hidden backside. So which part do we want to say is the base of this rectangular prism? Which side? That's the nice thing about rectangular prisms. You can pick this one here. So the one here, I'll outline it in red. We want to call that one the base. Okay. So we call that one that I outlined in red the base. So our volume is the area of the base times the height. So what is the area of that rectangle that I've marked in red? 6 times 12, right? Because that side's 12 meters also. So B equals 6 times 12, which is 72 square inches. And if we choose that side as the height, or sorry, that side as the base, what is our height? The height will be 5. This is the side that goes between the two bases, because my other base would be that red rectangle back there. So that would be my other base. So the height would go between the two bases. So the height is 5 inches. So my volume is 72 times 5, which equals 360 meters cubed, cubic meters. So that's a nice easy one. What's another name for a rectangular prism? Everyday shape. A box. It could be a cube if all the sides were the same. It's just a box. A rectangular prism is a box. So we're finding the volume of this box. Could be a cube if all the sides were the same. Then we could call it a cube. What's that? Right. So to be a cube, all the sides have to be the same length.
So a square prism.
A square prism? No, because you could have a square base and it could be really, 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 really tall. So it could look like a skyscraper. You could call it a rectangular prism or a square prism.
So when you figure out which one's the height, is it always the number that's not in the Asian deformity?
Yeah, that would be a good way to think of it. When we use to figure out the height, we're not using the height to figure out our base area, because it's kind of separate from the base. All right, let's do one that's a little more complicated. But after our opener, hopefully we have an idea of how to do this one. All right, there's this prism, and I'll connect these. There's my lines, the edges that we can't see. And let's say this side is 2 inches, and this is 10 inches. All right, so we want to find the volume. So what kind of shape is this? Hexagonal prism. So what is our base? The hexagon is the base. The base is a hexagon. So we need to find, we know our volume is the area of the base times the height. So we need to find the area of the base. I'm going to put that over here. So finding the area of the base means we have to find the area of that hexagon. How do we find the area of a hexagon? What's our formula? All those nice area formulas that we talked about last chapter coming back to be our friends again. Well, give us a hint. 1/2 AP. Apothem times the perimeter. So perimeter of the base. What's the perimeter of the hexagon? 12, right? Each side is 2 inches. We have 6 sides. 2 times 6, so 12 inches. Do we know the apothem? No? And let me erase these. And we'll draw the apothem in. There's my little triangle inside my hexagon. And what kind of triangle is this? 30, 60, 90. How long is this little piece here? 1 inch. And to go from the short side to the long side, multiply by the square root of 3. Need to write that a little. So the apothem, A, is 1 times the square root of 3. So we just get square root of 3. 1 times the square root of 3. So the area of the base is 1/2 the apothem, square root of 3, times 12. And half of 12 is 6. So we get 6 square root 3 square inches for the area of the base. So a lot like our opener, where we had an equilateral triangle, but this time we had a hexagon. So now we're set to plug into our formula. The volume equals 6 square root 3, that's the area of the base, times what's our height? 10. From one base to the other, times 10. And I multiply outside the square root, so I get 60 square root 3 cubic inches. And that would be my answer in simple radical form. Questions there? So the area formulas that we worked with last chapter, we're going to come back. We need to use those when we talk about prisms. We'll need them again when we talk about pyramids. All right, let's talk about cylinders now. Volume of any cylinder. Doesn't have to be a right cylinder. And the reason we do prisms and cylinders together is, if you remember back when we talked about the surface area formula, they're exactly the same. So exactly like a prism. So our volume is the area of the base times the height, cubic units. But for a cylinder, what is the base? What's the base of a cylinder? A circle. So the area of the base is pi r squared h. Usually you'll see it this way. Volume equals pi r squared h. R equals the radius of the base, and h equals the height. And we can say B equals area of base, which is a circle. So it's the exact same formula as a prism. But our base for a cylinder is always a circle, so we just have to find the area of a circle. All right, so let's look at an example. So here's we'll start off really easy. There's my cylinder. And that's 14 meters. There's my center. And this is 12 meters. And we want to find the volume. I'm going to say find the volume in terms of pi. All right, so our volume, pi r squared h. So what do we need to plug in here? What's r? 6, because we have the diameter here, right? 6 squared. The height is 14. So we have pi times 36 times 14. And I multiply 36 by 14 and leave the pi in there, so I get 36 times 14 is 504 pi cubic meters. And that would be my answer in terms of pi, or my exact answer. All right, questions on that example? Nice, easy one. All right, let's do another one. Last one. What if I have a shape like this? And this is 6 inches, and this is 11 inches, and this is 5 inches, and the whole thing is 17 inches. And our problem says find the volume of the mailbox. So what kind of shape is that mailbox? Is it one kind of shape? Two? What two shapes? We have a rectangular prism. Rectangular prism is this part, and a half a cylinder. So we have to find our volume in two pieces. We have to find the volume of the rectangular prism, and we have to find the volume of half the cylinder that's sitting on top. So we know how much mail fits in our mailbox. All right, so let's find the volume of the prism. So which side do we want to be our base here? The 6. So how long is this side? 12. And how'd you come up with 12? The whole thing is 17. This part takes up 5, so that leaves 12 inches for that side. I'm going to put that in red because we figured that part out. So that's 12 inches. So the volume equals area of the base times height. Our base is 6 times 12. And 6 times 12 is 72 square inches. So our height of our prism is what? 11, from one base to the other base. So the volume of the prism is 72 times 11, which is 792 cubic inches. Half cylinder. What's our formula for the volume of half a cylinder? Just find the cylinder divided by 2. So I'm going to say 1/2 of pi r squared h, half the cylinder. And let's plug in our numbers. Pi, what's the radius of the cylinder? Five, right? If I drew the cylinder in here, if I completed it, the radius of that circle would be 5. And the height of the cylinder from one base to the other, 11. So I get 1/2 of 25 times 11 is 275 pi. And when I multiply this out, I'll get a decimal answer. I get about 431.97 cubic inches. So the total volume is 792 plus 431.97, and I get 1223.97 cubic inches. So sometimes we have to break our shape into different pieces. All right, questions there? Okay. Homework.